Hello and welcome to the second part of this test take-up video series slash practice if you are not in the winter 2013 class. We're going to do questions 3 and 4, both of which are here on my Word document. And I'll come back to them in between the questions so that those of you who are practicing have a chance to see the question and then the answer. So without further ado, if you'd pause the video, I will go ahead and do the answer. Note to, there we go. Okay. So we want to check whether there's diminishing MRTS, and we want to find out whether there's return to scale. Okay, so the first thing I'm going to do is what are the returns to scale? Okay, so our test for returns to scale is whether some greater than 1 constant times the output gives you more, less, or the same than that same constant times each of the inputs individually. Okay, so our test for that is AY less than, equal to, or greater than, and that's what that sign means. I guess I should do this formally. F of AZ1 AZ2. Okay, so this F of AZ1 AZ2 is just some generic functional form that we've got a specific form for here, which is what you're being asked to show in the test. So I'm going to plug in this Z1 to the 1/2 plus Z2 to the 1/2 all to the 3/2 for Y. So I'm going to have A times Z1 to the 1/2 plus Z2 to the 1/2 all to the 3/2, and I want to know whether that's less than, equal to, or greater than. And now I'm going to plug in the functional form, and this is where those of you who screwed it up will have screwed it up, is by not putting the A inside of the power 1/2. Okay, all this is raised to the 3/2. And I guess I'll make all my brackets right. Okay, so now we're going to want to evaluate this to some way that we can compare it, because right now it doesn't really look like anything. Okay, so this left side stays the same. I'm just going to put little ditto marks rather than write it out again, but you can just follow it through. What we have here is A to the 1/2 times Z1 to the 1/2, right? I can just split those out and multiply everything inside by the original power, and that looks like an X, but it's an A. Z2 to the 1/2 all to the 3/2. Okay. In the next line, I'm going to factor out the A to the 1/2. Okay, and it's going to be multiplied by the Z1 to the 1/2 plus Z2 to the 1/2 all to the powers 3/2. Okay, so taking an exponent of an exponent, just multiply them together. Alpha to the 3/4 Z1 to the 1/2 plus Z2 to the 1/2. Okay, now I'm going to write down this original function again, because now we can say something about, sorry, I'm going to make this alpha prettier. Anyways, now we can say something about which of these inequalities is the correct one. Okay, so I have, sorry, this should also be to the 3/2 here. Okay, so I have both of these sides containing a Z1 1/2 plus Z2 1/2 all to the 3/2. So if I divide each side of the equation by that, I'm going to have A less than, equal to, greater than A to the 3/4. Okay, so we can tell, right, that it's in fact A is greater than A to the 3/4, right, because A is some constant greater than 1, which is why we make that assumption. Which means that if we increase the scale of our operation by factor A, right, we get A to the 3/4 increase in output, which is not as much as if we just increase the output by factor A, right? So therefore, decreasing return to scale. Okay, so that's the answer to the returns to scale question. Now let's look at the MRTS question, which was the first part of this. So I'm going to go to a new page, and it's y is z1 to the 1 half, z2 to the half, all to the 3 halves. So I'll write this out again. Okay, so let me just sort of give you an idea of what we're talking about when we're talking about diminishing MRTS. If I can spell. Okay, so the technical definition is that the isoquant is homothetic, or is, sorry, not homothetic, is convex to the origin, so it looks something like that. Don't need to worry about that. What we need is to show that, so the slope of this line, right, is the MRTS. Okay, so that we need to show that if we decrease Z1, that the slope increases, or that if we increase Z1, that the slope decreases. Okay, so how are we going to do that? Well, let's start out by getting the slope of this line, which is the MRTS. Okay, so MRTS is partial Z1 divided by partial y with respect to Z2. Okay, so just taking the derivatives of that, of course we have chain rule in here and we have all kinds of things going on. So dy dz1 is 3 over 2 z1 half plus z2 to the half, all to the power 1 half, right? Times the derivative of what's inside, which is z1 to the 1 half. So that's going to be 1 over 2 root z1. And this should be like that. Okay? And if you're clever, you'll recognize that z2 appears in exactly the same way in this function that z1 does. So the derivative is going to look largely the same. I just realized I forgot a subscript 2 there. Pop that back in. Okay, and now we divide them by each other. Sorry about that line. Maybe I'll fix it. Okay, so the first thing you can see is that this is just going to cancel out, go away. These 2's are going to cancel out. And since we have a z1 in the denominator in the numerator, it's going to be in the denominator, and we have a z2 in the denominator of the denominator, so it's going to be in the numerator, and that gives us root z2 over root z1, okay? Or square root of the whole thing, z1 over z2, okay? So we've got our MRTS. All right, now I want to find out how the MRTS changes when z1 changes. Okay, so I'm going to take dMRTS dz1. Okay, and since this is z1 to the negative 1 half, then that becomes 1 over 2, negative 1 over 2, root z2 times z1 to the negative 3 halves. Okay, which, since this number is less than 1, as we increase z1, MRTS decreases, right? So exactly what I was saying we were trying to show, that when we increase z1, the slope of this isoquant decreases. Therefore, since less than 0 for all. That's what that upside down A means. Z1 greater than 0, diminishing MRTS. And if you're interested and you want to, you could also make this diminishing MRTS conclusion based on dMRTS dZ2 being greater than 0 for all positive Z2. So if you want to show that, then that would be fine too. That also means that it's diminishing MRTS, right? Because we're increasing Z2 and the slope of this line is increasing, which basically means that this whole thing is a convex set to the origin. Okay, so coming back to the question set so that we can see question 4. I just realized how small that me doing question 3 is going to look on your video, so I'll make it bigger when I do question 4. So what are the conditional input demands for a firm whose production function is y equals z1 to the power 1/3 times z2 to the power 2/3? I apologize, this program doesn't have an equation editor. I couldn't make it pretty. So pause the video if you're new. And we'll go with the answers. That's better. I think my writing's probably the same size, so shouldn't be too big of a deal. So number 4. I always wonder if there should be an apostrophe in CIDs or not. Probably not, but I've seemed to always put one in there anyways. Okay, so if you aren't given a price ratio, you should always just assume that the price ratio is W1 over W2. This question seems to have that in the question on the test. Don't always assume that that's going to happen, because a couple years ago there was one where they weren't given and everybody tripped all over themselves, which is probably why this happened in the first place. So now we have, again, the production function. So the important thing to know when approaching any problem in microeconomics, this is not exclusive to this course, it's pretty much universal for the discipline as a whole, is that you're going to have a feasibility condition and an optimality condition. This is just sort of an aside. It's going to be really helpful for you to learn how to solve problems. Your feasibility condition just means that whatever solution that you come up with has to be possible, right? So while I would like to produce 1000y using 0z1 and 0z2, right, that violates this equation right here, and therefore it's not feasible. Okay, the optimality condition means that there's some rule that I have to follow that will make sure that the solution I come up with is the best I can possibly do. And you don't have to worry about deriving optimality conditions, you just have to worry about memorizing them, unless you intend to go on and do your PhD, and then you have to come up with your own optimality conditions, which is why they pay us the big bucks. Ha ha ha. So the optimality condition for a diminishing MRTS problem is that MRTS has to equal the price ratio. And someone figured this out a really, really long time ago. I don't even know who it was. But this is the optimality condition for this type of problem. Okay, your feasibility condition you were given in the question itself, which is the production function, right? So any y I want has to come from some combination of z1 and z2 that form this equality. Okay, my optimality condition somebody had to derive, and it's that the MRTS equals the price ratio. Okay, so let's start off by finding the MRTS. We've already been given that the price ratio is this W1 over W2. So we'll use those two things to solve for our conditional input demands. Right, and MRTS, of course, is dy dz1 over dy dz2. So just taking the derivative of this whole thing, it's 1/3 z1 to the negative 2/3 times z2 to the 2/3. Okay, and then dy dz2 is going to be 2 over 3 z2 to the negative 1/3 times z1 to the 1/3. And if you watched my video on conditional input demands, you'd know that we can do some shifting when we do finally divide these two things by each other. Namely, I can bring this negative exponent up to the numerator, and I can bring this negative exponent down to the denominator, which makes my MRTS equal, I'm going to cancel out these 3's, 1 over 2, and the z2 is going to be in the numerator, z1 in the denominator. Okay, and I've just said that that has to equal the price ratio. That's our optimality condition. Okay, because we can choose z1 and z2. So if I now multiply this through, I want to solve for either z2 or z1. Okay, so I'm going to solve for z2 first because it looks nice and convenient. So z2, I'm going to multiply both sides by 2z1. And that's my equation for z2 as a function of z1. Okay, so remember this is deciding my optimal amount of z2 and z1, right? But we also have the feasibility condition. So y equals z1 to the 1/3 times, and instead of z2, I'm going to plug in this solution for z2, right? Because z2 equals 2z1 w1 over w2 power 2/3. Now the nice thing about Cobb-Douglas production, right, is I have a z1 to the 2/3 here, and I have a z1 to the 1/3 here. So y actually equals z1 times 2w1 over w2 to the 2/3. Okay. Now I want to solve for z1 as a function of y because we know that that's what a conditional input demand is. And then once I've solved for it as a function of y, I can put a star on it. So I'm just going to multiply both sides by the inverse of this expression here. So it's going to be w2 over 2w1 to the power 2 over 3 times y. Okay? That is my conditional input demand for z1. Okay? So then I'm not done yet, even though it looks like I have some kind of solution for z2. This is not a conditional input demand. Why is that? Well, because it says nothing about my function of z2 as a function of y. So in order to get z2 star, I'm going to plug in z1 star instead of z1. 2, and I'm going to do this just to make it easier. It's all going to be times z1 star, right, which is w2 over 2w1 to the power 2 over 3 y. Okay. You may notice something similar here. This whole expression is just this expression to the negative 1. Okay, so I'm going to rewrite this. And again, this is just one way to solve this. There's a bunch of different ways to do it. This happens to be the easiest way as far as I can tell. It's w1 times 2 to the 2/3 times y. Okay, which means that I have similar bases. I can just add the exponents. w2 over 2w1 to the power 1 over 3, negative 1 over 3, excuse me, times y. And one last line just to clean it up is that z2 star equals 2w1 over w2 to the positive 1/3 times y. Of course, this would be acceptable. It's the same answer. I just like to clean it up and make it a positive exponent. If you're interested, you can plug your conditional input demands back into your feasibility condition to see if you get y. In this case, you will. In all cases, you should. And that's about all I have to say for this question. So if you come back for video 3, we'll do questions 5 and 6, which have similar setup, only different optimality conditions and different feasibility conditions because they're different types of problems. So I will see you for those.